Next, we will hear from the Director of Government Technologies and Strategies at Siemens EDA, Mr. Rich Pawlowski, on mitigating electronic design barriers.
Hello, my name is Rich Pawlowski. I'm with Siemens EDA. I'm responsible for the government technologies business. I want to thank, on behalf of Siemens EDA and Siemens Government Technologies, I want to thank Mark Rosker and the DARPA MTO team for the opportunity that we have today to discuss some of the electronic design challenges within the Department of Defense and how we're addressing those. We're going to talk a bit about Siemens globally and our government division. We're going to briefly review some of the trends and requirements that the defense world has been dealing with for years. And then we're going to talk about some of the solutions that the broader Siemens offers, not just the EDA group, but Siemens proper. Those include areas for trusted supply chain, digital engineering, heterogeneous systems, and security verification. Siemens AG is a global enterprise, about $100 billion in sales. Our fiscal year ends this month. The United States is our largest market with significant investment in R&D. Siemens Industry Software is the group that houses Siemens EDA, and most of you may know we have some global brands, areas like Team Center for product lifecycle maintenance, Sim Center, Ops Center, tools for physics-based analysis and design, NX mechanical design, and the group that I've been with, Electronic Design Automation, has some known brands within this industry: Caliber, Tessent, Veloce, Questa, Symphony, Expedition. Number one industrial software company worldwide. But if you look down to the right, we are working, Siemens Government Technologies, which has a special security agreement with the U.S. government, has some significant business here. Talk a little bit about Siemens Government Technologies. 300 employees, most of them cleared in Reston, Virginia, and have a variety of products, services, solutions. They're known for integrating various Siemens solutions across product areas and delivering them to the U.S. government. Siemens Government Technologies has served every federal cabinet level agency in the last 10 years. And if you look to the bottom left here, Siemens EDA is the newest member of the Siemens Government Technologies portfolio. Our solutions are now incorporated in that portfolio. If you look at some of the challenges that we've been dealing with, I think it was last April that it was publicly announced that microelectronics is the number one priority for the Department of Defense. I think it replaced hypersonics, actually. Many of you have been working on secure microelectronics for many years. There's a lot of risks in microelectronics, ranging from concept, design, which can happen in various places, third-party IP can come from outside of, secure facilities, etc., all the way through fabrication, testing, deployment, and the life cycle of the product. As you folks know, The FY20 NDAA 224 has required defense microelectronics products and services meet certain trusted supply chain as well as operational security standards to be in place by Jan 23. The FY21 NDAA also had language requiring, what we call measurably secure semiconductor manufacturing, packaging, and supply chains. So where does Siemens fit in with respect to aerospace and defense? So I think most of us who have been in the microelectronics industry for many years, we sort of view chips, ICs, SoCs, heterogeneous systems. We view them as the not just the heart, but definitely the brain of any system, including weapon systems. So there are 4 areas I mentioned where Siemens has what I call multidisciplinary solutions that cut across our different product groups well beyond Siemens EDA. Trusted traceability is about trusted supply chain, and in that supply chain, we've been doing a lot of analysis on how to deliver a broad-based solution, not just for microelectronics, but for the complete system. And we've identified some specific stakeholder types in microelectronics. There are more. We are in the process of developing solutions that apply trusted traceability to the semiconductor supply chain, so that we can look at the design, the manufacturing, the logistics, and the integration of microelectronics into the subsystems and systems, and not stop there, but deliver solutions that incorporate the entire program. Digital engineering is another focus area for the Department of Defense. I remember, I think we go back a couple of years to Will Roper's public comments about the criticality of digital engineering, model-based system engineering to the Department of Defense. At Siemens, what we call DISW, Digital Industry Software, we're looking at the digital twin from the microelectronics level all the way through to the system level, not just design, but through planning, engineering, all the way through service and life cycle. At Siemens, we also deliver the platforms. Teamcenter is a prime example, a product lifecycle management system that is used by certain agencies within the government to model and encapsulate the critical data that's required for the digital twin, at the concept level, through product, through production, and into the life for performance and providing continuous improvement and analytics capabilities to the systems of the future. Coming back to my area, Siemens EDA, I think there's been a lot of focus in the last few years, good focus that I've seen in the Department of Defense related to the electronic digital twin, even though emulation, hardware, software, co-verification, and co-design are not necessarily considered digital twin. Effectively, they are. I think in electronics, we've been practicing the digital twin concepts since our inception with the various abstractions of electronic, RTL, gates, GDS, etc. At Siemens, we take our electronic digital engineering capabilities, such as you'll find in Veloci for emulating systems and microelectronics. Here's an example where we use it. We have customers in the automotive industry that will take the Veloci platform, incorporate that into what we call the Pave 360 app that doesn't just deliver the core platform, but we partner with other Siemens divisions that bring other solutions to bear, such as Siemens Prescan, that provides, it can model traffic environments, scenarios, etc. These same capabilities are fully applicable to Department of Defense requirements for warfighters, and we also have the capabilities to connect the virtual modeling, the virtual system, to the actual sensors and actuators that are being activated by the system. So you can actually do a virtual model of your system, including all of the scenarios and actuation of the mechanics. I'm going to move on to what the industry calls heterogeneous systems. As most of you have seen, I think when we all started working, we were talking about many microns. We got into nanometers, and now we're seeing publicity around the next generation of semiconductor process technology being described by angstroms. Well, I think what we've also seen is that the premier systems players in the world, whether they're doing data center servers or whether they're doing the latest smartphones, have incorporated heterogeneous systems to optimize what in the DoD is called SWaP for their systems. So you see a lot of drivers and the same requirements in the DoD. You've got chiplets. We need access to that technology. We need to maintain the data performance that you would ultimately see in an SoC, and try to come as close as that to possible, and with a multi-chip system, which is more accessible, and technology today that can meet the requirements. Well, heterogeneous systems have their own issues. We've spent years trying to solve the system on chip, from concept to GDS to manufactured part, and now we're looking at, well, how do you do that in heterogeneous systems? Well, what's changed is we're now not just co-optimizing electronic and physical requirements, but we're co-optimizing areas such as thermal, stress, mechanical. How do you do that in the context of the available data, the available parameters that are specific to your system, and do an optimum co-design of a heterogeneous system? This is what the industry is after. Fortunately, Siemens, whether it's Siemens EDA, Siemens PLM, between our companies, our brethren, we have full solutions. Examples in Siemens EDA, I think one of the key requirements right now is early prototyping. We know there's going to be critical nets through a system. How do we look at those critical nets early in the context of a system, even before we understand, what's the pinout of the package? So how do we do some early modeling, planning, prototyping? It requires, again, co-optimization, not just of electrical parameters, but thermal parameters, mechanical stress, etc. Some of the other requirements of heterogeneous systems, I think key requirements are sign-off. When do you know that you have a system that meets all of your electrical specs and physical specs. So at Siemens, we, most of you are aware of the Caliber technology, the Caliber platform, which is really the sign-off standard for the semiconductor manufacturers. We have extended Caliber to provide sign-off, not just at the IC level, but at the IC package and assembly and MCM level, which effectively, if I think about the Department of Defense requirements, you're talking about low volume scenarios where the first revision needs to work. Just you know, we're not talking about high volume suppliers that have, you know, easy access to more MPWs, more, you know, instant turnaround on, you know, manufacturing incremental prototypes. We need something that is co-optimized and works the first time. So the last area I'm going to talk about is, you know, getting back into the EDA portion of Siemens where I am. If you think about EDA, you know, we have some strong competitors in EDA. You know, our brethren, Cadence and Synopsys. I would even include ANSYS in there as key players with large-scale portfolios. Siemens EDA, formerly Mentor Graphics. I wasn't supposed to say Mentor after January 1st, but I figured I'd fit it in once in this presentation. Siemens EDA is a full solution supplier. We start at high-level synthesis. We do edge design, circuit design, layout, functional verification, scalable verification, sign-off, test, yield, diagnosis, etc. We do it all. A couple of our competitors do it all. We have some specific differentiation, integrating with the larger Siemens. There's a lot of good technologies out there. One of the things we've done in the last, actually in the last year, if you look at recent acquisitions that Siemens EDA has made, these all apply directly to aerospace and defense. Ultra SoC, embedded lifecycle analytics can be used at design, early in design, and in test and in life. One-spin technologies, which is, you know, effectively formal proofs. And again, you can find formal solutions from various places, but one of the unique things about OneSpin is they have customized security solutions for specific platforms, whether it's RISC-V or others, that are incorporated by the DoD specifically in IV and V methodologies that I think we believe should and will be standardized over time to ensure you know, some of the security metrics that are being developed today. Fractal Technologies, another interesting player that we acquired a few months back. They are the industry standard for ensuring IP verification. If I think about the Department of Defense, I think one of the largest issues in secure microelectronics is third-party IP. We don't know where it came from. That will not change. Off-the-shelf products, off-the-shelf IP, we won't know where it came from. Fractal has technologies that allow you to prove that changes have not been made between abstractions. It can ensure consistency as you go through the incorporation of that IP and you know, the life cycle of using that IP within active programs. This really looks at how we've incorporated the ultrasoft technology, which we now call test and embedded analytics. And we have customers that are working with either Siemens EDA or PLM, looking at how do I create a system-level solution that can assess and analyze the life cycle data and optimize it and measure it, et cetera. So we bring in Siemens technology, Team Center. We bring in our low-code solutions with Mendix that allow quick development of applications to develop the requirements of these systems. In summary, I hope you have a better understanding of how Siemens interacts with the U.S. government today. We at Siemens EDA partner with the larger Siemens to offer full flow solutions that we believe will be critical for both product and supply chain security and provenance moving forward. If we can help or we can connect you with any of our experts, please contact Brett at Siemens Government Technologies, or give me a shout, and we can help you out. Thank you for the time. Thanks again to Dr. Rosker and the MTO team.
And now, presenting on Curation Drive Open Source Transition of the Open Road Chip Design Platform, DARPA MTO Program Manager Mr. Serge Leaf and Dr. Andrew Kang, Professor at the University of California, San Diego.
Hello, my name is Serge Leaf, and I'm a Program Manager at DARPA's MTO, or Microsystems Technology Office. Today, I will talk about Open Road Chip Implementation Platform. A few years ago, we started thinking about how to supply Department of Defense ecosystem with state-of-the-art design technologies and IP. It became apparent at the time that government ecosystem is not particularly well aligned with EDA and IP suppliers. It's not organized as a single purchasing or negotiating entity. There are diverse installations and business models even within the government ecosystem as it relates to dealing with commercial suppliers. And because the government doesn't really negotiate as a group, we end up with many different complicated, expensive deals, which essentially creates a barrier for the government ecosystem that prevents it from benefiting from state-of-the-art design technologies. So government ecosystem can benefit from open source, it was concluded, and specifically open source in design tools and IP. And so productized tools can theoretically be derived from the latest in academic research. Extensive and extensible capabilities are frequently needed by the government ecosystem to extend the base capabilities of the tools to take them in a direction relevant for the government designs. Namely, there are some secret capabilities that may be needed, and thus plug-in interfaces and secure cloud support are requirements for this extensibility element. And then to minimize contracting effort and predictable cost, we need to come up with some kind of model to provide support for the users in the defense ecosystem. So the question then this comes down to is, can some sort of curated open source distribution model serve the DoD constituents and perhaps ultimately the commercial customers as well? When we started the IDEA POSH program, there are actually two programs, IDEA and POSH. In IDEA, the goal was that we would create beyond state-of-the-art design technologies that would deliver no human in the loop 24-hour turnaround for a number of tasks associated with design of complex chips. And those included layout generation for mixed signal ICs, as well as, in general, multiple digital and analog back-end implementation technologies. On the IP side, we invested in creation of an IP portfolio where building blocks were developed that were open source and could complement the use of the IDEA tools. So we have multiple teams working on these two programs, and on simulation and verification, we have performers such as Sandia National Labs, Synopsys, Stanford, and Princeton University. On synthesis and optimization, University of Southern California, University of Michigan, University of Washington, and Yale. And on layout implementation, University of California, San Diego, University of Minnesota, University of Utah, University of Texas, Austin. And so how important are the two attributes of open source to different constituencies? The two attributes, the benefits that open source can deliver are low costs and beyond state-of-the-art features. And so how important are these to different groups of potential users? So if you look at large merchant semiconductor companies, they buy large volume of commercial licenses, they get massive discounts, and engineers basically have unimpeded access to all the tools they possibly need. And so the motivation related to cost savings associated with open source is basically non-existent there. However, there is interest in gaining access to features that may not yet exist in stable commercial EDA tools. Startups is another constituency to consider. They frequently benefit from deep discounting, and the tools become almost free for many of them, certainly before they attract serious funding from private markets. And so if you look at those companies, they're really focused on getting to near-term success, to proof of their concept, and so they can't really afford the time and risk associated with adapting poorly supported open source technologies. If we look at large commercial and defense companies, they do benefit to some extent from discounting, but they do need to control costs, and tool access is not exactly readily available at all levels to all engineers within those companies. And so there you start seeing, open source, the economics of open source may make sense for this type of users. And certainly the features that are being pushed forward beyond the state of the art can be quite interesting. In the government ecosystem, which really consists of FFRDCs and government labs, there's a diverse mix of installations and business models, and pricing for commercial tools is really high, negotiations and contracting really complex. And so there is really here a combination of economic benefits and access to beyond state-of-the-art technologies. So government ecosystem actually has high potential need for the type of technology that open source can bring to the table. But when you start thinking about open source, it becomes difficult pretty quickly, because if you were to put together a state-of-the-art commercial EDA flow, the choices of the tools that would go into the 4 buckets are pretty straightforward. They're dictated by the best-in-class solutions for each of these containers. But in the open source, you actually have multiple potential tools for every step in the methodology, and these tools are of highly variable quality and capability. So the open source design tools are really far from being equivalent in terms of capability to commercial flows. And one of the issues is that they don't fit well into pre-existing flows. Standalone or connection to other academic tools is basically the best we can hope for. The quality of open source products is also not great. Capability may be limited to demo designs. Nobody has ever tried any corner cases. And so these tools can be quite brittle. Customer support and training really doesn't exist. Graduate students that develop the technology typically come and go without necessarily transferring knowledge to others within their group. And so the customer ends up largely on their own if they undertake use of open source. There is no distribution channel. In other words, nobody is particularly motivated to promote and drive adoption here other than by word of mouth and classical open source communities. And so the question here is our stellar performer in this program, which is called Open Road, is that an exception to the rule, or can other open source programs achieve similarly spectacular results? So Open Road may be an exception. It may be an indication of how to proceed forward. It has shown near state-of-the-art capabilities, and in some cases beyond state-of-the-art capabilities, on over 100 tapeouts. Open Road is floor planning, place and route, essentially full physical implementation of integrated circuits. If you look at flows in digital and analog realms of IDEA, you see that this place and route technology participates in both of those flows. It has demonstrated commercial and open source flow integrations. It is moving towards cloud scaling for further improvements in performance and quality of results. It has numerous tapeouts in commercial and DoD spaces, and Open Road team has been able to support quite a few end users. And there is growing public awareness of this technology, and that in turn is driving the usage momentum. So can this momentum really be translated into curated operational model? That's a great question that a person running this team, Andrew Kang at the University of California, San Diego, will address in a presentation that follows me. Thank you.
Good afternoon. My name is Andrew Kang from UC San Diego. I'm here to present the Open Road project on behalf of a really amazing team. The ERI recognized from day one that we face a crisis of design. Taking innovative ideas into silicon runs head-on into barriers of cost, expertise, and risk. The cost of a wafer pretty much always ends up at a nickel or a dime per square millimeter. But this curve says that the cost of designing that square millimeter is out of control. And this hardware design crisis has created a crisis of innovation. Our nation has got system innovation talent and software engineering talent in spades. There's a synergy here since hardware designers really write code in the Verilog and VHDL hardware description languages. The real crisis is that innovators can't tell how good their code is in terms of the metrics that they care about: size, weight, and power, and performance. Fundamentally, this is because it's just too difficult for them to take their ideas, their Verilog and their VHDL codes, into silicon. How do designers today transform a piece of Verilog or VHDL code into a manufacturable chip layout? Well, commercial EDA vendors offer extremely sophisticated tools that have thousands of commands. These tools enable bleeding-edge customers to squeeze every last bit of performance, power efficiency, and area density out of a foundry's technology. But the tools are difficult to master. You need expert users who perform many manual steps, and there is schedule cost and risk, and this is the crisis of design. The Open Road tool can deliver a layout that can be sent to the foundry in 24 hours with no human in the loop. Our focus is on ultimate ease of use, leveraging core innovative technologies such as partitioning, machine learning, and parallel optimization. Thus, our project directly attacks the crisis of design and the crisis of innovation. Schedule, we run in 24 hours. Expertise, it's a no human in the loop tool that outputs design rule clean layout. Cost, it's free open source. Why does this matter? Because this unleashes innovation. Teams can move forward with system ideation and design space exploration friction-free with almost zero overheads. And especially for government and the defense industrial base, OpenRoad enables ownership of a more agile, transparent SoC design process behind firewalls and customizable to application needs. Our tool performs the RTL to GDS chip implementation flow, starting with logic synthesis and ending with a GDS2 tape-out database. A year ago, we showed a V1.0 tool with a modern integrated EDA tool architecture, industry-strength database and timing analysis, scripting interfaces for users, plus design rule clean layout generation in GlobalFoundries 12LP process. This year, our V2.0 tool brings new features with high value to users, such as early chip package planning and parasitic extraction to feed timing sign-off. Our users have qualified OpenRoad quickly on new commercial technologies, and we've enhanced other aspects of the user experience, including the GUI extensions that you'll see in a few minutes. We've also had quality of results, power, performance, and area, or PPA, as a key focus. OpenRoad's automated layouts are now faster and denser, the equivalent of a technology node of improvement in this past year. And we recently added true no human in the loop auto-tuning that finds better tool configurations than our own human expert users. This year has also seen use of OpenRoad for tapeouts of user designs. Over 100 tapeouts on Skywater 130 nanometers, an SoC tapeout in GF 12 nanometers, and Army Research Labs has a project in flight for Intel 22 FFL. Overall, we now support the range of foundry technologies that you see here, and users are running our tool on other processes as well. Last year's tape-in proof point was a version of the University of Washington's Black Parrot SoC. The RTL to GDS flow is now down to under 5 hours, and quality of results improvements versus this past fall are quite significant. Here on the left, you see a reprogrammable AI platform in GF 55 nanometers, and a reprogrammable AI computing tile in GF 12 nanometers from the Army Research Lab using OpenRoad. On the right, the FASOC team, led by the University of Michigan, made a GF 12 nanometers tape-out that included this OpenTitan SoC with integrated temperature sensors. All of the physical design and timing optimization was done with OpenRoad. OpenRoad is the heart of the ASIC design platform from eFabless called OpenLane. This has been used in the design work for 100 tapeouts in Skywater Technologies' 130 nanometer process. And this past July, eFabless transferred their OpenLane flow to the OpenRoad project. Here are the images of the first 2 shuttle runs in the Google Skywater program. OpenRoad is also the default EDA solution in eFabless's commercial offering called Chip Ignite. We'd also like to highlight the traction that has been achieved with a broad community of users and developers. Our users range from novices to experts. Their applications include trust, 3D IC, and AI and machine learning, to name just a few. The plots that you see here show daily statistics from a 2-week period at the end of July. These metrics of our community and engagement with the project are all growing. For instance, the upper plot shows nearly 1,000 downloads a day from nearly 4,000 unique GitHub users. Our project is easy to find, our repositories on GitHub, a nicely automated flow, and the integrated app, as we call it, which is the EDA tool. Some tutorial videos are online as well. Next up is a demo video showing OpenRoad in action and what it brings for its users as well as contributors: design insight, timing debug, visualization of core algorithms, and delivering DRC-clean manufacturable layout. The main message is that OpenRoad has the architecture, integration, and user interface of a full-fledged EDA tool. The voice you'll be hearing next is that of Matt Liberty, who's one of the key EDA industry veterans on our team.
Here we see the IBEX design routed on TSMC 65LP, and we'll use it to examine how OpenRoad lets you walk through your design and explore it in more detail. So if we zoom in on any particular part of the design, we can select an object. For example, this wire is connected to this net with this name. We can zoom to that object, and if I turn off the routing, it'll be a little clearer. You can see the highlight is present. We also have an object inspector. So this net, we can inspect it in detail, seeing its properties and its connections. In this case, the blue represent hyperlinks, so we can switch to see there's the driver pin of this net, and we can switch to the instance associated with that driver pin. To get more information about it, we can see that it's being driven by this NOR gate. So this lets us walk through the design and continue the traversal if we want. We can go through where is this A input coming from and what net is that, and so forth, allowing us full traversal. In addition, go back to the full view, we have a find dialog. So we can find all the clock buffers in the design and highlight them here, marked in green. This lets us see these selections that are chosen. We can see all of them here in the highlight set. We also, in addition to highlighting, can do a simple find. So I could find all the nets named clock and simply select them. And you can see your clock tree, and the green dots that are highlighted are the clock buffers in the clock tree. So these are different ways you can use find, select, highlight, and the object inspector to fully explore your design. Here we see the fully routed swerve wrapper design on the GF12 process, and we can inspect the timing. Click the timing button, which will bring up a list of paths in the top half. And for each path, as we select it, we can see the individual stages of that path. I'll turn off the wires to make it a little clearer. And if we click on a path, we can see this red highlighting is the path. And we can select individual pieces of that path, which if we zoom in, we can see are highlighted. This is the timing view of OpenRoad. You can choose to see either setup or hold and configure the number of paths shown. Here we see the JPEG design on the ASAP7 process immediately after CTS has finished, design is placed, and I've just run the global router. And we can look at congestion for routing by turning on the congestion map. There's also a congestion setup that lets us set the number of bins that we're going to see. So we can get a look at the congestion in finer detail. We can also change the range of congestions displayed. So if we want to see only the 50 to 100% congested regions, we can change the limits to highlight and bring out the detail there where we can see the strongest measures of congestion. You can also look at H and V congestion separately. So in this case, the H congestion is fairly similar, but the vertical congestion is quite a bit less, which is an interesting aspect of this design that could be investigated further. The congestion map lets you zoom in and see in detail each of the individual G cells and explore where the routing congestion is. This can be very helpful in designs with macros or tight channels. OpenRoad can be used to understand algorithms and visualize them in detail, enabling developers and also users to gain insight into how the tool works. Here we're looking at global placement, and this is the initial placement phase of global placement where we can see these objects are being placed according to a wire length minimization criteria, and you can pause and continue. The pausing and continuing can be user controlled to be fine-grained or more coarse-grained. So you can see the evolution of the algorithm and its placement. When we reach the end of the initial placement step of global placement, we're now ready to resolve density overlap. Clearly, there's all these objects have been placed in a very tight location. So as we continue, now the Nesterov algorithm will take over and it will seek to resolve density overlap while continuing to minimize wire length as best it can and meeting those two objectives together. So we can see the kind of gradual expansion. And when we hit a pause point, we can actually zoom in. The GUI is fully live. We can select an object, see what it is, get information about it. Here we are printing out some gradient information. And we can continue the algorithm. That selected object remains selected, and we can watch its evolution throughout the algorithm as here we begin to expand out, resolving density constraints and watching the algorithm proceed. It will shortly call the global router right here because we're running in a routability mode of placement. Because we have an integrated platform, the global placer can call the global router since they share a common database, get back information on congestion, adjust its metrics to try and resolve that congestion as it continues global placement. This is the advantage of a fully integrated platform as opposed to a set of point tools, that the algorithms can cooperatively work together, achieving a placement result that considers multiple objectives. And of course, here we see it's globally placed. Next step in the flow would be detailed placement that would continue forward and legalize these results. The Open Road platform's goal is to be able to produce fully manufacturable GDS. This means we have to obey all the design rules, both in the detailed routing as well as we need to obey manufacturability rules like metal fill. So here's an example of a small GF12 design. If we turn on a single layer and we zoom in, we'll see that there is a fair amount of white space between the wires, that this may not meet the density requirements for manufacturing. So Open Road provides a metal fill capability. So I can turn on the fills. You can see these additional shapes are added. I'll toggle them once or twice just so you can kind of see they're slightly lighter colored. And you can see we put in a variety of sizes and shapes, some rectangles and squares, some thin stripes. Basically, we try and use larger shapes to fill up bigger empty spaces and smaller shapes where they're required to fit into small spaces. But by having a metal fill capability, we are able to meet the density requirements of the manufacturing process and therefore produce a tape-out ready GDS. This is one of a large number of rules that the system must meet, both in detailed routing and in manufacturability for an advanced node like 12 nanometer global foundry process or the 7 nanometer ASAP process.
Open Road has made a number of breakthroughs and more lie ahead. We've delivered advanced node tape-out capability from an academic research project. The tool is built to last with industrial strength foundations like the database and the timer. Version 2.0 has improved quality of results and made a lot of improvements on the path to intelligence and being a self-driving tool. Users are taping out designs across a range of foundry technologies. We're very encouraged by the contributors from major companies and DoD. This has always been part of our vision for Open Road as a foundation for research, design, and EDA innovation, and transitions beyond the ERI. We are going into the last year of the IDEA program, so for us, growth and transition are paramount. Open Road can serve an ecosystem, businesses, researchers, and the government's special design needs that may not be best served by today's flagship commercial tools. We'll continue to grow our technology, especially to better leverage machine learning and cloud deployment. And we'll be growing our community. We'd really love to learn more about how Open Road can best serve folks in this ERI audience. And so on behalf of a great team, thank you very much for your attention and for your support.
Welcoming back to the stage, DARPA MTO Program Manager, Mr. Serge Leaf.
I am Serge Leaf, and I'm going to deliver a brief overview of the DARPA Toolbox initiative. DARPA Toolbox initiative has been started about a year ago, and with the goal of providing low-cost access to design technologies to DARPA performers. Commercial terms that are typically offered by commercial suppliers of design tools and IP come at relatively high cost and have complex licensing and legal frameworks associated with them. And that, in a way, prevents many of the DARPA parties executing on DARPA research contracts to access state-of-the-art design technologies. So this has resulted in frequent choices of non-optimum flows when these parties design ASICs and system on chips to satisfy the program requirements, and also introduced execution risks and complicated transition because people gravitate to low-cost solutions that do not require them to solve the problem above, which is complex access to commercial tools. So we have been building a list of partners who have joined the DARPA Toolbox, and some of them are shown here. Since the creation of this presentation, there have been several others that have joined, and they can be seen on the website that we created for this initiative. When the initiative was announced, it turned out it was actually quite popular, and we got a large number of views. And since then, we've had more or less steady stream of parties approaching us about either adding more products and technologies to the toolbox, or with questions from the performers and DARPA proposers on how they can access those technology assets. So the benefits to suppliers for participation in the toolbox are relatively straightforward. They get early visibility in leading-edge research, they gain insights into next-generation product requirements, they get to establish new tool and IP-enabled capabilities within the DoD community, and since they are present in the programs before the transition phase, they stand to actually have some potential business upside when the program transitions out of research and towards the next stages of deployment, experimentation, and ultimately productization. And of course, they get benefits from strategic marketing and gain visibility into what DARPA is doing, and they get some PR benefits here as well. To performers, the benefits are even easier to quantify. They get very straightforward, low-cost, scalable access to state-of-the-art tools and IP, which they can use for the purpose of performing on DARPA programs. We remove potential roadblocks that currently impede the speed of innovation. This program essentially requires simplified and predictable legal terms to be available to our performers to streamline the acquisition procedure. And all the licensing essentially occurs at the team level. So the toolbox agreements are typically executed by the prime contractor and cover the entire team, meaning all subcontractors on their team. So the process will look something like this. At the industry day, the program manager presenting a new program may discuss relevant toolbox suppliers in their presentation. They may explain the general structure and terms of the business model associated with the supplier that may be relevant or interesting for their program. And the CMO or contracting representative who speaks at the industry days will also include the summary of toolbox suppliers as well as the process for accessing those technology assets. A prime proposer would then execute an NDA or non-disclosure agreement with a relevant toolbox supplier if they decide to use their technology or technology assets. Prime would then engage with the toolbox supplier in conversations related to technical planning and pricing. The toolbox supplier is required to offer the pricing and business model that we've negotiated to all the proposers. So Toolbox supplier would then issue a quote that's consistent with this pre-negotiated business model, and the prime would then include this pricing in their proposal document sent to DARPA. So if selected, the prime and the Toolbox supplier will execute a licensing agreement, and the Toolbox partner will deliver products, licensing, support, maintenance to the prime and the team members. None of this stuff passes through DARPA, and this becomes a relationship between the supplier and the DARPA performer, where DARPA's value contribution was limited to negotiating business model terms and legal terms to eliminate the unnecessary work in this area by the performers. So with the initiative as it's been going on, we are always looking for proposers and performers to start in earnest using the technology available in the DARPA Toolbox. And as far as new partners are concerned, they're also welcome to email us at toolbox@darpa.mil, and we will start the conversation that will lead to them being in the toolbox. Thank you for listening.
This concludes our morning presentations. During the lunch break, please visit the exhibit halls to engage live with performers and view technical posters and demos via chat and video.